let's look at how the splitting occurs for tetrahedral geometry complexes. So this may be a little hard to see, but none of the orbitals point directly at the ligands, right? So remember the ligands are along the z, the x, and the y axis, and notice that this is where the ligands are, but the orbitals are pointing between them. So the E sub g orbitals, that set of three orbitals, it overlaps with the ligands much less than the T sub 2 G set. And so these orbitals have been renamed to relate specifically for tetrahedral geometry. So instead of using the same name, we call E sub G E and T sub 2 G T sub 2. So this is how the split occurs. So it's flipped, basically, right? Those three orbitals were lower in energy for octahedral, but they're higher in energy for tetrahedral because those two orbitals, they overlap with the ligands less than the three orbitals in this T sub 2 set. So they're lower in energy. So we have a smaller crystal field splitting compared to octahedral complexes. And this is the magnitude of, or quantitatively, how the two relate, right? Where the splitting, crystal field splitting for tetrahedral complexes is 4/9 of the splitting for octahedral complexes. So the main thing is to remember is that these orbital sets are flipped and the crystal field splitting is smaller for tetrahedral. Now, pause this video and answer this question here. So if we have a metal with 5 unpaired electrons in the d orbitals, how many unpaired electrons will we have when these 5 electrons fill in these orbitals? How many unpaired electrons will a tetrahedral D5 ion have? So pause this video, think about it. So it turns out there'll be 5. There'll be 5, right? Because the crystal field splitting, this is really small. So this is not a big energy hump that the electrons have to overcome. So they're going to fill in one by one first before pairing. So we have 5 unpaired electrons. Now let's look at splitting for square planar geometry, right? Which, if we compare it to the octahedral geometry, basically it's the same minus those two ligands, right? Or they were in the transposition along the z-axis are removed. They are removed. So this increases the stability of the z-axis because we don't have ligands, we don't have the electrons from those ligands repelling the electrons in the d orbitals. They aren't there. So that stabilizes the z-axis, and it or increases, stabilizes or increases the stability along the z-axis, and it decreases the stability along the x and y axes. X and y axes. So the splitting is a little more complicated for a square planar, right? We have splitting into 4 orbital sets. 1, 2, 3, 4. With this first orbital here being the highest in energy, and these 2 orbital sets being the lowest. and it's like a stair step in between. Okay, we're gonna pause here.